I did my graduation from IIT Roorkee, and afterwards I worked for a company called DE Shaw. And those people who are from US, they would be aware about DE Shaw. So at DE Shaw, we managed big data before the term was even coined. When I say that, that means hundreds of terabytes data we were managing in 2002. We had a 10,000 nodes cluster in 2002. All right. Afterwards, I started a company called Tvits Global and built an enterprise-grade document management system. And we sold that to many companies. So that using that software, around 30 power plants in India have been constructed. All right. So I sold my stake and joined a company called InMobi because I was more interested into the data technologies and everything. So I built a recommender using the standard procedure, but we faced a lot of interesting challenges during the recommendation. Okay, so I built a recommender churning around 200 terabyte data at InMobi, where instead of showing ads, I was displaying the apps. I was displaying the apps which user can, which instead of apps, I was displaying, ki, hey, you are playing this game based on your history. These are the recommendations for you. And then I joined a company called Amazon, where we built our own stream processing engine, so which is being used by many teams. So that one was an accidental discovery. I was trying to do optimize this image which is shown on the detail page. And to do that, we needed a kind of stream processing, and none of the solutions existing were on the lines of what we needed. So that time I built our own stream processing. So that's a bit about my background. So now you can be assured that I'm not from a completely theoretical background. So we have dealt a lot of things in terms of big data and parallel computing. So and last year I started Know Big Data in a hope to part a lot of knowledge on big data and do a consulting on big data. As of now, we run CloudX Lab and Know Big Data. On CloudX Lab, we give lab access to all the students, okay, to all the third-party instructors, okay. Third-party instructors, when I say companies like Simplilearn and others. So that's a plan. So I'm going to open up for all the individual in the retail as well, the CloudX Lab, so that everybody across the globe can access a centralized platform to learn all these big data technologies. And I'm going to make sure that it is going to be extremely cheap, as in everybody should be able to afford. Not something like $150 a month, but like $10 a month. So that's about CloudX Lab, cloudxlab.com. All right. All right. So let me have a look at the question window. All right. So do you have any questions for me before we start? All right. All right. So everyone, please feel free to ask as many questions you want. Okay. Great. Great. All right. I'm hoping that everybody is able to hear me clearly. All right. All right. So I mean, at Google, I'll because most of these technologies, most of part of the Hadoop has been done at Google. I mean, in terms of they publish the paper, and so as part of this Hadoop distributed file system, people call it DFS, distributed file system, or HDFS. As part of these file systems, the most important thing that was done was breaking down a file into chunks and distributing across the cluster. All right? Or multiple files of a folder are distributed in multiple hard disks across the whole cluster. When I say cluster, multiple machines connected to the network. All right. So as part of Hadoop distributed file system, the most important thing that was done was dividing the storage in the cluster, right? I hope that is clear to everyone. So the biggest utility of Hadoop distributed file system is it divides the files, or as well as it splits the bigger file into smaller files and distributes the storage to the whole cluster. Okay, so that you don't have to do it manually, it does it internally. Now, once you have divided the data, how do you process it? How do you do the processing? That's where the compute engine comes to play. Okay, so also the definition which I'm going to stick to everywhere with the big data is the data for which you require distributed computing. I'm being rash, I know, when I define big data, but I'm going to stick to the definition that big data is some data for which you require distributed computing. All right. So distributed as in multiple computers attached to each other either via network or some other means, so to achieve this common goal. So that is something called distributed computing, and I'm going to stick to that part. Now coming back to the compute engine, after Hadoop distributed file system, that's probably the most important component of the Hadoop ecosystem. All right. So this component, let me quiz you a bit. How fast can 1 gigahertz processor sort 1 terabyte data? Anyone? Quickly. And when I say 1 gigahertz processor, it has got 2 GB RAM, and it got 10 billion names, 10 billion names to sort. Anyone? Yes? And we are not using solid state hard drives, we are using normal hard drives. So how fast can 1 gigahertz processor sort 1 terabyte data? When I say sort, ordering them line by line such that the one which is starting with A is above the other one. Okay, so how much do you think would it take? I'm asking not the approach, just the time estimates. Okay, if you want to unmute if you want me to unmute you, just raise your hand quickly and I'll unmute you. All right. Rana, okay, Rana, I'm making you the panelist. All right. And what else can I do to convert this talk into a discussion? All right. Yes. So anyone? Just give me a rough number. Even if your answer is 100% wrong, 100% as in instead of 1, you are saying 2, it's completely okay. So even if your answer is 2 standard deviation away, 1 standard deviation away, I'm okay. Anyone? All right. So the answer is 6 to 10 hours easily. I mean, here I'm actually being optimistic. It's nothing you can compute about. It's more about experience. So the most important thing we need to understand is that the hard disks are slow. Okay, hard disks are slow such that 1 gigabyte, reading 1 gigabyte data from the disk takes around 5 seconds, which means reading 1 terabyte data is going to take 5,000 seconds. Okay, so if you have, and then writing the data is around 10 times more costlier. So effectively, when you go into terabytes size data space, the computing does not take comparatively as much time as the reading and writing data takes. Okay, even if you are just counting characters, even if you're just counting characters from left to right, top to bottom in a file, still it's going to take huge time. All right. So the other aspect of the computing engine, other than other than distributing work, is to make it read fast from the disk. All right. So question is, why are we worried about this kind of number of hours? So when I say when sorting 1 terabyte data is taking 6 to 10 hours, what's wrong? Okay, we need faster sorting, bigger data sorting, and do it more often. So that's basically the reason why do we need a compute engine in first place. All right, so to divide the work amongst many computers, we needed a compute engine. Let's say you come up with this idea that, hey, you have 200 terabytes data, and all you want to do is you want to find a particular line containing a particular keyword, or you are just looking for those lines that contain a particular keyword. And mind it that you have 200 terabytes data in which you want to search for this keyword. So what will you do? You will have to basically divide the work amongst hundreds of computers. You will say, okay, first 10 files let this first computer do, and then let the second computer do some work, then third, and then fourth. So you'll divide the work of searching in the file uh, by yourself. You will write all that mechanics, right? And that's where exactly the Hadoop MapReduce comes into play. He says that you don't have to take care of all that mechanics. Let me help you out. So keeping that in mind, in Hadoop 1.0, MapReduce was introduced. This was in Hadoop 1.0. Okay, I'm explaining this so that it's easier to explain the Yarn framework. All right, and please keep on asking. Okay, keep on asking questions as much as you can, and yeah, do not worry about whether you will be right. Is it a good question, bad question? Yes, Shiv Kumar, you want me to unmute you? Just put it on the questions window. All right. So keep asking questions. Do not worry about whether I'm right or wrong. Okay. So keep asking questions, whether it's a bad question, good question, whatever. Okay. All right. So let me describe what does it mean by MapReduce. In in HDFS, the way you have a master-slave architecture, whereby one of the computers you make as admin node, and rest of the computers you make as data node. While name node keeps the bookkeeping, does the indexing of which data is where. It maintains the record, okay? This particular file's data or is on these machines, and this particular file's data is on that machines. So that kind of records, name node does it. And for everywhere, whenever you want to find out anything about files, you generally go to name node. All right. So it's a kind of master-slave architecture whereby one computer, one machine, one particular process is called, you run at name node, and rest are called data nodes. All right. And when we say name node, data node, all of these are basically Unix processes or operating system processes, whereby they listen on a particular port and respond to the queries asked on that particular port. All right, standard networking. So for example, email server runs on 25 port, general web server runs on 80 port. When you open the browser, you are generally talking to a web server running on 80 port. All right, in the same way, name node, data nodes are all the processes. So that answers most of the questions like, can we run data node, name node on the same machine, or can we run multiple data? So it's all up to how you configure them to run on which port. As long as ports are not clashing, you can run as many of those. Okay, but it doesn't make sense to run multiple data nodes on a machine. All right. Now, in an HDFS, you had this architecture so that you run data nodes on all the computers in the network and divide the files equally, or try to divide equally by with the help of name node. Name node basically help you distribute the files across the cluster. All right. Now your data is spread across the cluster. All right. Now what you want to do is you want to do the computation on the same node, and that's where the MapReduce 1.0 came in. MapReduce 1.0 said that, okay, there will be a machine called job tracker, or there'll be a process called job tracker whose primary responsibility will be talking to the end user. Okay, so end user asks the job tracker, hey, get my work done, and job tracker divides the work and distributes it in the cluster. Okay, so that was a strategy, and job tracker will keep pinging all these task trackers to understand their state. Okay, whether a task tracker is up, down, and all that. And this work, so for a particular, say for a particular MapReduce job, for each job tracker will break it down into multiple phases, multiple tasks, and will keep on assigning to these task tracker. In case any task tracker breaks down, it will reassign it to somebody else and abandon that particular task tracker. So this is how the work division started in MapReduce 1.0. Okay, now the problem was this job tracker was only talking to the end user in terms of maps and reduces. You always gave this guy the list of map function and reduce function and input data. That's what you always talk to the job tracker earlier. And since many kind of things were possible, somebody wanted to talk in terms of SQL, somebody wanted to do anything else, but everybody wanted the work to be divided across the cluster, because division of work itself is a humongous task. Think about division of work. First, this job tracker has to keep track of all the machines that are up. This job tracker, has to understand that what is the capacity of each individual task. Also, it has to track that, okay, who is doing what and who is busy with how much. Okay, and also what is the RAM size of each machine, how much load can each take, those kind of resource information this job tracker tracks. And whenever it gives the work, it takes the output back in case something fails. So all of these mechanics of job tracker, task tracker was very important for not only somebody who is talking in terms of MapReduce, but also somebody like who wants to run a process, say HBase. HBase wanted to run a database where the work needs to be divided amongst multiple computers. So basically many kind of work, not only one kind, MapReduce was part of this was to be done using MapReduce framework, and that's where this Hadoop MapReduce 1 was becoming the bottleneck. Because everybody has to convert their work into a certain MapReduce way. Okay, even if so, it's like if you have a hammer, it was considering everything as a nail. So, I mean, The only way you could distribute your work was writing maps and reduces, which is not great for every kind of circumstances. Somebody wants to run a continuous query. Somebody wants to, there are many, many kind of requirements from people. And MapReduce 1.0 was not able to cater to. Instead, people started thinking that, hey, we will write our own system. We'll write our own system which will divide the work. So, but remember that when you write your own system, you will have to install it on the machines, right? If you have 8,000, there are so many companies, and every company has like 1,000 node of cluster, or somebody has 500 nodes, somebody has 200 nodes. Now, if you come up with a new framework, you will have to install your slaves all across the cluster, and that was impossible. And that's what was solved by, so this is the model how initial job tracker worked. And this client was giving the work in terms of map reduces, and job tracker was delegating to various tasks, various task trackers. Task tracker was having multiple tasks, doing multiple things for you. Okay. All right. And the only way the client was talking to the user was talking using the client to the job tracker was in terms of map reduces, which was not a good way. Okay. And that's where the Hadoop 1.0 was not helpful. So Hadoop 1.0, the map reduce part of it, somebody took out the MapReduce part only from MapReduce framework in Hadoop 2.0, and rest of it, like process management, we became Yarn. Now that opened the doors for everyone. That opened the doors for everyone, be it MapReduce, be it others, and others were like dramatically the next day. I mean, in coming next 6 months, there were every system, every tool ported to Yarn, because HDFS is still the prominent storage. And on HDFS, if you want to get something done easily, you have to get it done through the Hadoop, right? So already lots of people had a good adoption of Hadoop already, and that was probably the best system at that point. So even today itself, because of Yarn, Hadoop has survived. Okay, now you can see here that Yarn, earlier there was only one thing. Okay, then it became many more things. It's like refactoring of the code. And if you understand refactoring, what does it mean? It's it's basically breaking a big function into a small function so that the small functions could be used elsewhere as well. Similarly, MapReduce was broken down into MapReduce. MapReduce 1 became MapReduce 2.0 plus Yarn. All right. On top of Yarn, there are so many systems. Even Tej, HBase. This is something which will surprise you, that even HBase runs on Yarn. When you query HBase, it basically uses Yarn to query the network. Even when you do the MapReduce on HBase, query goes to HBase, and HBase breaks down the MapReduce in its own way and queries through the Yarn. So that's a kind of a wave this refactoring led to. All right. So Yarn gave the support for the workloads other than MapReduce. Okay. Earlier there was one system, you can think of it this way, that earlier there was this system which could only talk to you in terms of maps and reduces. Okay. And that kind of workload was very limited. That's, we call it workload, because if somebody can talk to you in terms of only one language or only in one paradigm, then it becomes difficult to talk, right? If I want somebody to do me work, it's like okay, so uh, if like for cook, I can only give him the work of cooking, right? And that's what is the limiting factor. Similarly, in case of earlier MapReduce 1.0, we could only give the, all right, so give the MapReduce work. Next was the scalability. It was not possible to have multiple different resource managers earlier. And that's why that was not scalable. Compatibility with MapReduce, that's a beautiful thing Yarn guys did. They said, okay, we are upgrading from MapReduce 1.0 to 2.0, but whatever you did with 1.0, it will work seamlessly. All you need to do is please recompile your code and then launch it. That's it. That's what they asked for. Please recompile your code, and that's all they wanted. And all the code which was written for Hadoop 1.0 was still valid for Hadoop 2.0. Nothing was changed other than recompiling. All right. Next was it improved cluster utilization. Of course, when you have multiple different kind of services using the cluster in a different way, your cluster is better utilized. Agility, of course, and then MapReduce was batch oriented. That was too limiting. Okay. Any questions as of now? All right. So MapReduce 1.1, this is vaguely the categorization. Okay. And I would like to dive deeper into Yarn afterwards. So the job tracker was what? Somebody who a client talks to and says, hey, get my work done. Job tracker is like um, supervisor of a workshop. In a workshop, there is many people who are working on different aspects. And the supervisor is the one, you give the work to him, he says, okay, don't worry, I'll get it done. And he goes to his workshop and says to somebody, hey, you have to do the welding, you have to do this, you have to do this, you have to do this. Okay? And when everything gets done, it reports back to you, sir, your work is done. All right? So that is job tracker. While task tracker are independent people, independent experts, technical experts who are able to get, who do the actual work. Okay, so the job tracker took many shapes. One job tracker, one was like centralized job tracker, which is resource manager, and the rest became application masters. Every different kind of job, there is one application master. All right, all right, and then there is timeline server and all that. Okay, so you can think of it this way. Now this looks a little complex to most of you, and I'll spend a lot of time on this slide. Okay, so here what you can see is that the role of job tracker has been taken by resource manager. All right, role of a job tracker has been taken by a resource manager. The client comes in and says, hey, I have got my own manager who can get the work done through your job workshop. So the client comes with something called application master, who is a domain expert. All right. So HBase is one client for resource manager. So HBase comes to resource manager, hey, you know what? I know my work. I know how to get it done. Just execute this guy on one of your node, my application master, all right? And the application master takes care of all the work getting done, all right? So you can think of application master as, uh, think of it this way, that when the client comes in to talk to the resource manager, so resource manager you can think of as if it's it's a, what do you call, it's a prime minister of a country. Okay, every node's owner is like chief minister of a country, a chief minister of the state. So every state's information is headed by the chief minister 1, chief minister 2, chief minister 3. Okay, so you can think of these as three different states, and you can think of this guy as the prime minister. All right. Now, an external organization comes and says, hey, I want to put sugar factories in this country. Okay, they go to resource manager, which is prime minister, and says, hey, I want to get my work done on of the sugar factory. Now, when they talk to the Prime Minister, he says that, okay, you can talk to these three. I believe that for the kind of space you are asking for sugar factory, you should talk to the chief minister of this particular state. Now, the chief minister of this state will allocate somebody. So we'll say, okay, fine, you can establish your head office here. Okay, and that head office, I can provide you all the resource and the areas which you need. Similarly, at the same time, resource manager, which is the prime minister, he says that, okay, fine, I can also give you the some more place in different states. All right. So when you want to get your work done, you come with your own manager and you establish your own firm here in the form of application master. Now let's take the analogy to the real use case. Spark came along. There was no such thing earlier called Spark. Spark came along. Spark's client talked to the resource manager and say, hey, you know what? I want to get my work done. I know how to get my work done, but I need the resources from you. So resource manager says, okay, fine, you can establish your Spark application master. Okay, so this is your Spark application master, or you can think of this one this time. Earlier, let's assume that this one is HBase. This one is Spark application master, and the resource manager told him, okay, since you wanted three nodes or three tasks to be executed, I'm giving you three more containers. Okay, so application master will take it from there and will start its own surveys, talk to the containers and every. So if you think about it, this application master also runs inside container and the actual task also runs inside container. Okay, so every time you want to get something executed from resource manager, you give him first the application master, and the application master can further request resource manager for more resources. All right. So any questions at this point? I hope I have not confused you or something. Yes, go ahead. Hassan, have a question. All right, I'll just put your question on the notepad so that everybody can see. Hi. Can you see, is this font good enough for everyone? Great, great. Hassan, I'll unmute you if you want. Okay. All right. Or okay. I'm
Unmuted.
Yeah, go ahead, Hassan.
Hey, hi, Sandeep. If I are you able to hear me?
Yeah, I can hear you.
Okay. My question is, you are saying like for each application, it is going to create one application master, right? A type of application.
Right.
Okay.
Correct.
If I submit like two, three MR jobs only, map reduce jobs only. Like suppose I submit
Yeah.
one job at 9 o'clock, another it's still running, and another
Yeah.
at 10
I got
o'clock,
your
which is
question.
still. So in that case, it's create a new application master, or only one application master is going to suffice the MR jobs. Yeah.
Okay, very good question. Very good question. Thank you. I think I'll answer it. So his question is, I'll mute you.
Yeah. Okay. Thanks.
Okay. All right.
Muted.
Yeah, great question. Great question. His question is, all right, a little recap. So when application comes in, he talks to the resource manager. Okay, and then resource manager asks him, hey, where is your application master? And what kind of resources do you need for application master? And then um, resource manager allocates that kind of resources and starts your application master. And from then onwards, the work is taken over by the conversation between application master and resource manager. Afterwards, resource manager, this application master you created talks to the resource manager to release more resources, and then it says, okay. So now, question is, what if, what if I as well as Hassan has submitted MapReduce task, or I submitted MapReduce task, and that MapReduce task is still running, and then again I submitted another one. All right. So that's an interesting question. So that I'll discuss here. All right. So basically, the question is, what is the lifespan of the application master? What is the lifespan of an application master? So when the client is requesting the resource manager, it gives the request in the form saying, hey, my lifespan of the application master is infinitely running, or it should be killed after 15 minutes. All right, it cannot be more than 15 minutes. Or as well as in the job specification which client requests to to the resource manager, it says that, hey, this application has to be one per user, which means if Sandeep Giri is launching MapReduce task, the application master for Sandeep Giri is going to be different from Hassan. Okay, so if MapReduce asks for one application per job. Okay, second is one application per workflow or user session, meaning you have started a user session now, and again you're starting that after some time. Okay, so because in each session, imagine this: if you have created a MapReduce job itself has multiple phases of execution. In first phase, it will send maps to be executed, and then reduces. Then there are multiple tasks to be executed, right? And afterwards, it will do the accumulation. A lot of work has to go. So, and similarly, in the case of Spark, where you have a continuous connection with the end user, if you continuous connection between the client and the server, in those cases, will it keep creating every time I launch a small function in my Spark code? Will it every time create application master? No, because because while starting the case, Spark tells the resource manager, hey, you know what, this particular application is going to run as long as the user has opened the connection. Okay. Third is long running application, which are infinitely running application, such as HBase, Apache Slider, or Impala. These are always on, which means once their application master is created, don't create them again. Okay. All right. I hope I have been able to answer your question. Hey Ben, and all right, I want to see. I want to ask more questions. I want to answer your more questions from you. All right. Let me try to. Okay. All right. Next great question is, does Yarn handle dynamic resource allocation? Yes. Okay. And I'll go into that in a minute. All right. That's a good question. All right. Now, again, a little bit. So I hope everybody is clear about this. Node manager is generally per node agent. Okay, every node has to have a node manager. Application master is per application, while resource manager is single in the whole cluster. All right, and application master is single across the cluster, and so the examples are, there could be one application master for MapReduce, one application master for Spark, and so on. So application master is the one who manages the whole dynamics for individual application. All right. So I hope this structure is clear. Basically, instead of resource manager managing the whole work, it says that I will just take care of giving you the resources or connecting you to the node managers where you can execute your stuff. Okay. Afterwards, whatever you do, as long as it's illegal, as long as it abides by the constitution, it's okay, you can do. All right, and that kind of policing is done by container. Container makes sure that application master or any of the tasks do not violate any privacy concerns, such as the application master cannot cannot access any of the files which it is not allowed to, which the user is not allowed to access the files. It cannot access those files. Similarly, the application master will not be able to execute a process using some other user's credentials. So those kind of sandboxing is done by container. Container makes sure the security is intact. All right. Now here is the workflow. The workflow goes like this. The client comes to the resource manager and then submits the job. Then the next step is client comes to the resource manager. Resource manager creates the application master, and then conversation between application master and the resource manager starts. So client came in, then resource manager created application master, and the conversation between client and application master and client application master and resource manager starts happening. Okay. And so basically the application master registers with the resource manager and client can now talk to them. Afterwards, if application master says that, okay, I'm the representative of the client, now I'm going to do a couple of things, and application master starts directly communicating with the resource manager, and resource manager starts providing him the resources. Okay, so application master asks for containers, and application master launches these containers. So these are the containers for this red one. I think it's red. I'm not sure because I'm a colorblind person. So and this application master is, I think, blue. So those are for that. And application master doesn't have to have the containers on the same node because it wants to process the data on other places as well. And then the all right. So once the whole process is done, this application master shuts down after deregistering itself from the resource manager. All right. Now this is another way of saying the same thing. Application client came to submit a job to resource manager. Job contains the full yarn application, meaning that also means that if your Hadoop cluster is running very well and you want to execute a Spark work, you don't need to install Spark on every node. Okay, that's a very important point which you can take away from here. When if you want to install, if you want to run a Spark job on your cluster which is already running Hadoop 2.x, you can simply run the Spark. You can submit a Spark application to the resource manager, and from then onwards, in that description of the application, it will be written that this class or this program is the one which needs to be executed as application master. Okay, so the first thing resource manager does is it creates the application master inside a container, and then application master starts talking to resource manager, and the whole dynamics keep on happening all the time. So you can see clearly that the resource allocation is fairly dynamic. All right. So whosoever is asking yarn or whosoever is asking resource manager for resources, they release a kind of a request. So you ask a resource manager that, hey, I want these many containers having this much memory probably, these these many CPUs, and I also want the containers which are closer to these files, that is locality constraint. I can ask Yarn that, hey, give me 50 containers closer to this particular file, or give me as many containers as this file is closer to. Okay, so I can put as many constraint or as I want on the request. Okay, or I can just say to Yarn that, hey, give me 20 containers, whichever it is. There's no locality constraint, there's no memory, there's no nothing. I can just say, give me these many containers having this much RAM probably and one CPU. That's it. Okay, so That's a kind of request format. And then, or you can say, okay, I don't have a parameter right now for the containers. Right now, just give me one container for application master. Rest, application master will keep on requesting you again and again. As and when application master gets a workload, it will ask you again and again. So I don't have a specification. So that's exactly what is meant by dynamic allocation, as Benjamin asked. Okay. All right. So again, the application lifespan also. So one is the resource request. You ask for two things. One is, I want these many resources and run my application for this period of time. You can say that my application should be run for each user separately. For each user, it may be that for each session, you want to run it separately. Okay. Which means that you opened one console in which you started Spark, and then you opened another console where you started another Spark. There will be two Spark application masters. All right. Now, I hope this is clear to everyone. This is a good question from Pradeep. Question from Pradeep is that does application master interact with each other, since app master is hooked up to the node, and when that node is down, how the failure can be handled? Good question. Good question. So when these kind of circumstances arise, let's take case of how should I all right. When these kind of situation arise, let's say HBase master, secondary master, primary master, you generally have this nice tool or nice system called Zookeeper. Okay. So to make these applications master interact with each other, you rely on a third-party service. Okay. And that coordination, whether one application master is up, other is down, and what is exactly happening, that you generally manage using third-party system such as Zookeeper. For example, HBase uses Zookeeper to interact with available reason servers. Reason servers are running inside containers. So, okay, let me not confuse you. So, most of the service in the Hadoop ecosystem, when they want coordination, because coordination is required because nobody is sure where is their process running or whether their process is running or not. Okay, so it's like we and all of you on WhatsApp. Okay, and we want to have a kind of hangout quickly, or we want to have something of that sort. So what we want to do is we come up with a plan that, okay, whenever we all of us are online, just update here, just update uh, in WhatsApp with your name that, hey, we are up. Similarly, when these all machines want to talk to each other, all these processes want to talk to each other, so all they do is as soon as they are up, they write their name in Zookeeper, and from there they can read and know about everyone in the cluster. So they all of these processes use Zookeeper for that kind of work. All right. I hope I was clear, Pradeep. Did I make sense, or I just blabbered? I think. All right. You want me to unmute you? You have more questions? Brilliant question. All right. All right. So if you want to write your own Yarn application, my suggestion would be try to use existing frameworks first, such as MapReduce, Spark, maybe HBase, maybe Storm. Storm also run on Hadoop. And if that's not sufficient for you, okay, then you think about, say for example, Spark guys realized that MapReduce was not good enough for them, and they proved technically. So then they went ahead and tried to build the system from scratch. If you are not able to use MapReduce Spark, try to utilize existing tools to build systems, such as using Apache Slider. You can run existing applications inside on the Hadoop. Second, if you second, you can use the Apache Twill to wrap your application and run it on the Yarn cluster. Otherwise, if you realize that none of these systems are fitting your bill, then you go ahead and build from the scratch. And this one called distributed cell application, which is a bundled Yarn project, will come as a very great example for you. Okay, we are also trying to build our own terminal right now in the browser, so we're trying to go with this distributed shell application. Okay, so this is the way you can build your uh, own cluster, own Yarn application. All right, so that's pretty much. If you guys want, I can give a demo of my CloudX lab, and otherwise, yeah, I can take more questions now. So, all right, Ben, was I able to answer your question in due course of discussion? All right. Since questions are not available, I'm just copy pasting whatever he's saying. Okay. If you want me to unmute you, I can unmute you if there is no noise around you. So this is from Ranjit. Okay. Ranjit. Okay. All right. Now, question from him is that Yarn has inherent fault-tolerant process to resubmit the job. Okay, yes, that's right. Yes. Or Zookeeper is necessary for fault tolerance. Okay, very good question. I will answer this. Okay, and then Ben, I'll unmute you for your question. If okay, all right, very good question. So, question is that if fault tolerance here means multiple things. Okay. All right. So the kind of fault tolerance Yarn gives you is that it reports to you that your task has failed. Do you want to restart it? Okay. You can say yes, or you can, while submitting itself, you can tell that keep running until fails. Okay. So that's one kind of fault tolerance. All right. But when it comes to coordination, such as that if there is some already process running, okay, don't run this process. Okay, which means that you need to know about all of the processes running, and which also means the only either you have this ability to query the whole cluster, or if you have the ability to modify the other process such that when they start to work, they write their name on this whiteboard. Okay, like me and you making calls to all the customers. Okay, and when I'm talking to somebody, I write their name on the whiteboard so that you don't call him. And when you're calling somebody, you write their name on the whiteboard, and so that I don't call them. So that increases, that makes it possible that we don't call the same person at the same time. Okay, so that's a coordination. That's a coordination, and that coordination is very much required in distributed application. For example, how does HBase know how many region servers are available in your cluster? How many region servers are down? Because HBase has two parts. One is HBase master and HBase slave, right? Now, how many slaves are up, how many slaves are down? Instead of you pinging all the slaves, let the slaves write their name on the whiteboard. Okay, and then you keep on looking at the whiteboard and see, okay, these guys are there. And this whiteboard has special properties that after 1 second, their name might be deleted. Okay, so that they have to keep putting their name again and again, and that will ensure that these only those people's name remain on the whiteboard who are alive, who are working. So that's a very important aspect of the zookeeper. Zookeeper provides such kind of disappearing name uh, in the this thing. Okay, so it's zookeeper is more like a whiteboard where everybody writes their name. Okay, all right. Was I able to answer, Rajit? No. All right, all right. So, all right. I think he's able to uh, get his answer now. All right. So great. So Ben, can I unmute you? You had some question. All right.
Hello, everyone. So the
Hey
question I
Ben.
asked earlier, that was in the mind that, sure, if you're using Spark, Spark has to know probably um, how many containers it's going to request based on the typical jobs you want to ask and how much memory to allocate. But
Hmm.
in a case where you have an on-premise cluster or you have certain cloud allocation for your cluster,
Hmm.
is there a way to make Yarn allocate as much CPU resources as possible to carry the job faster? And when another job comes in, what happens? So basically, if this cluster is fully loaded, how
Hmm.
does Yarn handle a new job
Good.
incoming?
Good. Great question. Great question. Great question. So yeah. So there is one more aspect which I forgot to mention, and thank you for bringing it up. All right. So the question is, there is one more construct which Yarn provides, and that's called queues. Okay. So every job has got queues. So every job defines that, okay, I belong to a particular queue. So that so the work in a queue is always in the sequence, while work in two queues is done parallelly. Okay, so if there are so okay, here first. So Yarn provides you this construct of queues. You can create as many queues, or this sysadmin can create as many queues as they want. And in a queue, if you submitted the work before me, unless the previous work finishes, the next work is not going to be executed. Okay? Executed unless there is resources available. Okay? So basically, it is very much possible to basically one particular task consuming all the resources. Okay, it's very much possible, but the yarn will parallelly execute even if, let's say, there is two CPUs available in the cluster and you have asked for both the CPUs. All right, and you have also asked for a particular amount of RAM. Okay, so it is high chances that you will consume all of it. Okay, but if there is another, so first, Yarn provides containers, so you cannot consume more memory than container can allocate. Okay, so that's also configurable. And second part of the thing is that if there are multiple requests that have come in for the same resource, and if they have come in from the same queue, they will be queued one after another. If they have come from different queued, they will be executed parallelly. if the containers are available. If the containers are not available, there is no chance. So yes, theoretically, it is very much possible that one resource will consume the entire cluster. One particular app master can consume the entire cluster and do not leave the space for others. All right, even if the others are in different queue or in the same queue. But the way we do the things is that we create queues so that the different people can execute things in parallel and some execute in sequence, so that the cluster does not reach to a situation where everybody has clogged the system. Okay, so I hope I have been able to answer your question. His further follow-up question is, FIFO in case of resource lock? Yes. All right. So generally, that's why these application masters, individual application master can cause a resource hog, okay? Can cause a resource hog provided if it's not built correctly. Okay. Also, the other way of avoiding resource hog is by configuring your yarn cluster such that the container does not consume more memory than you want it to. Secondly, creating a maximum number of containers, putting a upper cap on the number of containers it can create, the number of tasks each node can execute parallelly. Okay, so that is the way to avoid this kind of resource blockage. All right, Pradeep's question is, can we set priority when this situation occurs? So basically, I think amongst the queues you can create a priority queues. Okay, amongst the queues you can create a priority queue. Good question. All right. Good. If the client submits a job and all the node managers are busy, will RM will keep it queue or will it will keep it in the queue? Okay. I could have demoed you this part. And just that, yeah, just that we have just resolved that same issue. Okay. Good questions. Great set of questions. Hassan's question is how to make single application master not to use resource from whole cluster. Okay, so the one is that the application master has to be kind of trusted. Okay, has to be kind of trusted. And so a single application master can use the resource from whole cluster actually. The only way you can control is by controlling number of, by controlling the maximum resource can an application master consume. That you can configure at the yarn level, and you can also configure at the yarn level that how many resources can go into in how many containers can be given sorry, how many CPU or how many containers can be executed on each node manager, that you can control. And that I need to find out if we can restrict number of containers per queue. I think you can restrict number of containers per queue so that one queue does not consume the entire cluster. This I need to find out. Okay. All right. Great set of questions. All right. And probably I should be able to answer your question once I implement my current running this thing. I'm trying to create a kind of a terminal. We have a terminal in our courses. We generally provide something called CloudX Lab. Okay. So in everybody's learning management system, we have this part coming from CloudX Lab so that we provide a web console so that everybody can just log in into the system and start using it. Okay, so here, for example, so this is the login and this is the password. So I'm logging into one of the nodes. Okay, so for example, right now this terminal is in the browser, but this terminal is not inside Yarn. This terminal is basically running on one particular node. So here I'm running the Spark, and from here I can start doing things like sc.parallelize and 1, 2, 3, 4. So this is an example of a Spark task. So the moment I start this PySpark, right now I started the client for Spark. This is the client for Spark. And if you see here, if you go from top down, it says that the here it has started the security manager. Okay, and then there'll be a state, yes. Here started remoting, started listening to on this particular address. So it says that it has started listening on this port, and this is generally, okay, generally starts when the application master is done. And you can see here it is saying that the application master wait tries and all of that is done. So this starting HTTP server, this is part of each application manager. Okay, each application manager of this Spark uh, stays as long as we are connected to it. Okay, and it has also started this Spark UI, which actually tells us the current state of my Spark jobs. Okay, this currently tells us the current state of my Spark jobs, what memory we have consumed, how much it is running, and everything. So, for example, sorry, I actually screwed up. I screwed up. All right. So I can say A equals to sc dot parallelize, and then I'm just making it parallel. All right, and then I can say define my function called am, which is just doubling something. It's just saying x into x. This is making this square, and then I can just run this function, on the whole cluster and create another. So here, when I say b.take, then it will start talking to Yarn and get the work done. Right now it's not. Now it has started. So what I wanted to show you first is when I start this process, one thing it has done is it has started this Spark UI, okay, which is running at this one. This also blocks the other systems to be running at the same time. Okay, and also this, sorry, other reason for Spark UI is that the same UI, since it's running on the same port, the other people can talk to it. Other Spark jobs can talk to this and submit their work. Okay, so your question, Rajit, would be probably answer better in terms of this. So when a job starts, it can start its process, or when application master starts, it can start a process at a fixed port. Okay, if it's not able to start that process, maybe somebody else is running there, then it can talk to that process which is running there and then get the work, get it there. But the problem is that what if I'm running on e.cloudx.com, somebody runs on f.cloudxlab.com, then there may be parallelly other Spark UI existing. So there are multiple ways of coordination between application master and others. One is using Zookeeper. Second is by talking to Yarn itself, asking if there are other instances of the application master. Third is by using the Zookeeper. Okay, so those are the of uh, ways of interacting with this. Now, when I did some execution, you can see that it has started the executors. Okay, various task executors. These will be running on the inside the containers on the nodes. All right. So it was a quick demo. I know that I have missed out a lot of details. Okay. All right. So any other questions for me? All right. Hassan, was I able to answer your question regarding the particular one? I think I need to do a little bit more research. So that was a quick and dirty demo. Yes, yes, you can reach out to me. This is my email ID somewhere. You can just, my email ID is, I mean, better thing would be either reach us at No Big Data, put it there, and put Sandeep in CC. Okay. I'm still struggling to manage my information, so okay. So if you have a question, just put to both of them. All right. And so that's pretty much from my side. If you have any questions, please feel free to reach me at just put both these email IDs. All right. Because there's generally some person who is attending to most of my emails, so they can have a look at your email quickly. And yeah. All right. So that's pretty much from my side. All right. So I know that 1.5 hours is quite small for this kind of discussion, and but this will give you a good starting point. And Jayant and Hassan, since you have started the recording, please share the recording as well. Okay. I have not started the recording and I forgot to start. All right. Thank you, Ben. I'm happy that you liked the session. All right. Okay. Okay. Hassan, you will get the notification to convert the video recording and then you upload it in your YouTube. It's okay to upload it in YouTube and yeah, and just share with us. It's okay to make it public. All right. And all right, just drop that on the WhatsApp group so that everybody can keep it. All right. Thank you, Pradyumna. I'm happy that you liked it. And please feel free to stay connected. And I know I'm not great with the WhatsApp group. I keep on just reading it, but I am not able to cope up with so much. All right. Great. Thank you, Siva. Thank you, Kota. Thank you, Pradeep. Thank you, Pradyumna. Thank you, Sayesh. Thank you, Arun. Thank you, Tohir. Thank you, Benjamin. Thank you, Senthil. Thank you, Pavan. Thank you, Riaz. Thank you, Chinmay. Thank you, Sachin. Thank you, Hassan. Thank you, Jayant. Thank you, Rana. And yes, stay connected. All right. Great. Great.